My name is Louise Daly, and this is my final project for my Advanced Analytics Applications class. I want to give a little disclaimer. If you hear my dogs in the background, I'm so sorry. There's nothing I can do about it. So the title of my paper is Decoding Stellar Classes Using Machine Learning, Spectroscopic Applications in Astrophysics. I chose this topic because upon completing my master's program, I plan to pursue a PhD in astrophysics. And whenever I have the opportunity to select my own research focus, I try to make it a priority to explore topics that align with my long-term career goals. So if this topic seems kind of out of left field for the scope of this course, I hope that explains it and makes a little more sense. I had a lot of fun with this project because it allowed me to combine my passion for astrophysics with my growing knowledge and expertise in data science. I also want to preface by saying my research paper ended up being 32 pages long. So I've tried my best to keep my presentation short and sweet. Okay, so what is stellar classification? Stellar classification is an essential task in astrophysics as it helps scientists understand stars' properties, their life cycles, potential for hosting planets, and other things. Traditionally, the process used to be done manually, which was slow and tedious and prone to human error. But now much of the process has moved to being automated machine learning processes, which is really cool and exciting. So my project explores how machine learning can automate and improve stellar classification using data, specifically in my case from the Sloan Digital Sky Survey. I'll talk more about that in a minute. So the main goal of my project is to classify stars into their spectral types, O, B, A, F, G, K, M. Using different machine learning models. So those letters right there, stars are grouped into 7 main classes based on their temperature and color. The fun little mnemonic that we use in astrophysics to remember the classes are, oh, be a fine girl, kiss me. So in my study, the data that I pulled, we actually don't have any B-type stars, so just to get that out of the way too. This is just a nice little graphic I provided talking about the spectra and how it relates to the star classes, their color, temperature, just to kind of give you an idea of what we're getting into. So, research objective, I focused on answering 3 key questions, which are, can machine learning accurately predict a star's type? Which features are most important for stellar classification? And how do different machine learning models compare to each other in their performances? To explore these research questions, I used a combination of supervised learning algorithms such as logistic regression, random forest, and gradient boosting, and unsupervised learning methods like k-means clustering. So, what is the Sloan Digital Sky Survey? I'm going to refer to it as SDSS because obviously that is a mouthful. So SDSS is a massive astronomical survey that has mapped millions of stars, galaxies, and quasars since the year 2000. The telescope used collects photometric and spectroscopic data using a 2.5 meter wide-angle optical lens telescope and spectroscope, and it's located in Apache Point, New Mexico. And here's a picture of the telescope. So types of data collected. The SDSS provides a multitude of different types of data, but the main types I used in this project are going to be the photometric data. Photometric data measures the brightness of stars in different wavelength bands, U, G, R, I, Z. Those are different filters. And then the spectroscopic data, this is when you capture the light spectrum of stars, and it helps determine things like the temperature, chemical composition, and motion of the stars, things like that. Honorable mentions for data that the SDSS also collects but I didn't use are redshift data. Redshift is just like how fast objects are moving away from us due to the universe's expansion or moving towards us due to the motions of celestial objects. It also collects imaging data and calibration data, but none of that is specifically relevant to classifying star types, so I didn't use them in this study. Here is just an image of the SDSS redshift map of the universe. I just think it's really cool, and if you look at about 7 o'clock, you can see the white arrow pointing to the Milky Way center. So if you can imagine about 26,000 light years away from that, you can actually wave hello to yourself. Okay, bad joke. So the data For my project, like I said, I used the SDSS, but specifically I used the Milky Way mapper data. The data set size originally is over 5 million stars, but I selected a sample of 5,000 just to make life easier. And then here, I just list out the variables of interest in a little more detail. But going on to the next slide, I'm just going to go ahead and read through these key terms just so that we're all going into with on the same page. So photometric magnitudes, as I mentioned, this is just a logarithmic measurement of the brightness of a celestial object. They help us determine the star's temperatures. And then spectroscopy is just the study of how light interacts with matter to determine a star's composition and temperature. Basically works imagine like a prism separating light into different colors or wavelengths or bands, just depending on how you want to word that. The flux values measure the amount of light that a star emits at those different wavelengths. And then the spectral line strength measures the intensity of the specific emission lines, and this is what helps us identify the temperature of the stars. So for data pre-processing, of course, I had to clean and pre-process the data set to not only ensure quality and consistency, but also to get it down to a manageable bite-sized set. Some of the data cleaning I performed includes data querying and filtering. So for the photometric and flux data, I was able to use the Python tool AstroQuery to pull the data directly from the SDS website right into Python, and it was really easy. For the spectral line strength data, I ran into some issues getting a hold of that. I had to actually use the SDSS Sky Server SQL website tool, and I tried to merge these two data sets. They were not compatible, so I ended up doing my project in kind of two different pieces, one with the photometric and flux data, and then another part with the spectral line strength data. I also had to handle the missing data, so I removed any of the stars with incomplete photometric or spectral data. I removed the outliers, excluding the extreme values, unreliable readings. And then for feature selection, I had to remove any unrelated variables like the ID tags or what I mentioned earlier about the redshift. So we're focused only on classification relevant features. And then, of course, I had to standardize the data, scaling the numerical features just to kind of ensure the consistency across my different models. So getting into the exploratory data analysis, before selecting features for my machine learning, I started by exploring the data sets to identify potential patterns and relationships. And I conducted a lot of different types of EDA. This is in my paper, and I have a multitude of different ones. I'm not going to include all of them here for the sake of brevity. But things that I will mention is I made histograms of the photometric magnitudes. So these display the distribution of the brightness values across the different wavelength bands. It helped identify trends and outliers that needed to be removed in the photometric data. The distributions also help provide insight into the range of observed brightness values, and they help determine appropriate feature scaling methods. So that was really useful. I did some pair plots to visualize how different features of the photometric data was relating to each other. This made it easier for me to detect correlations and the potential clusters. And then for the PCA scree plot, this helped to determine how many principal components to keep by showing how much variance each component explains. It was obviously very useful in the dimensionality reduction. And then, let's see, going on. The first thing I did in my EDA, I wanted to include this here, is that I created this bar chart for the top 10 most common stellar classes, just to kind of get an idea of what the data was looking like. And as you can see, some of the subclasses dominate, creating the class imbalance. I noted that this may impact classification accuracy, and as we'll get to at the end, if you keep in mind the A-type stars, we're going to come back to that. And so I created a couple of different heat maps during my EDA, but this one examines the correlation between the photometric magnitudes and the color indices. I have highlighted here is that the color indices capture differences in the brightness across bands. So imagine the photometric magnitudes. These are the actual mathematical differences between the bands. So the key takeaways for this are that there were strong correlations observed between the adjacent photometric magnitudes. This suggests that some of the features provide overlapping information. So since the highly correlated features can introduce redundancy, this analysis helped kind of guide the feature selection by ensuring only the most informative values were used in the models. These correlations kind of help me refine my feature set and improve the model performance. So supervised learning, I did the logistic regression as the baseline model, and then I did random forest and gradient boosting. The logistic regression was not complex enough to handle this kind of complex data. So as you can see, the random forest performed the best. It had the highest accuracy, making it the best model for classifying the stellar types. The color indices and the spectral flux, H alpha, H beta, and O3 were the most important features. Just a quick note, I go into detail about these spectral flux values in my paper, but I just wanted to mention here that O3, it just means doubly ionized oxygen. This is just oxygen that has lost 2 electrons due to the energy excitation. So the Roman numeral 1 represents a neutral atom, so the 3 just means doubly ionized. And as I already mentioned, the logistic regression really struggled due to the complexity of the data. So moving on, the unsupervised learning method that I chose to utilize was the k-means clustering. This was really great. I was actually really pleased with how this turned out. My first k-means clustering before I removed all of the outliers was not very satisfying. So to get this scatter plot looking so nice and beautiful, I had to obviously remove the outliers. This improved the cluster cohesion, making the groupings more distinct and nice to look at. So if we look at cluster 0, this is the primarily cooler type stars, K and M with the weaker emission lines. And then cluster 1, we have mostly hotter stars. This would be O and B type stars, but as I said, there's no B type stars in this data set. So cluster 1's only the O type stars. These have stronger H alpha lines and also the O3 emission lines. So cluster 2, these are the intermediate stars, F and G type stars. They have moderate spectral strength and flux values. So this analysis, reinforced the unsupervised learning can identify meaningful structures in the astronomical data even without labeled classification. So this was really nice. I really like this one a lot. Okay, so for the final classification table, after training all my different models, I generated a final classification table to kind of summarize the results of what I was able to do. So you can see here on the left, that's just, the tag, the ID tag. Then we have stellar class, and the encoded value is how many I was able to classify. So the model successfully classified stars into the 6 spectral classes. Remember, we didn't have any B-type stars. They're absent from the data set. So O, A, F, G, K, and M. Although you can see here that I actually didn't get any A-type stars. That's why I wanted to note from the beginning of the presentation where I mentioned that the class distribution being off, right? So the model performed best at classifying O and M-type stars, likely because these occupy the extremes of the temperature spectrum. O stars are going to be the hottest, and M stars are going to be the coolest. So again, the A-type stars, they're the most difficult to classify, suggesting potential overlap in the spectral properties with the nearby classes being dominated. So the classification table, it provides insight into how well the machine learning can differentiate stellar types and highlights the areas for potential improvements in the feature selection and model tuning. So overall, the machine learning did successfully classify stars using this photometric and spectral data. And then as we mentioned, the random forest was the best performing model. It achieved 67% accuracy. It Definitely outperformed the logistic regression and gradient boosting. I wish I tried hyperparameter tuning to get it a little more accurate, but this was the best that I could get. And I mentioned that in my paper too. The color indices and the spectral flux values were the most important features for classification. And then again, the k-means clustering revealed meaningful stellar groupings, confirming that spectral features naturally align with stellar classification, which is exactly what I was expecting. Challenges and limitations. Here we go. Challenges and limitations. The class imbalance that I mentioned, it obviously affected the accuracy, particularly for the A-type stars, which were harder for the model to distinguish. And again, the B-type stars were totally missing from this data set. I started with 5 million, I narrowed it down to 5,000, and it just so happened that I didn't get any B-type stars in there, so this limited the classification coverage in that aspect. Some stellar classes had the overlapping spectral properties, and we see that in the EDA that I performed. This makes it more difficult for them to differentiate between the classes. So future work, I thought, maybe implementing deep learning models like CNNs could improve the accuracy by learning complex spectral patterns automatically. However, I didn't implement any CNNs for this project because I don't have much experience with them yet, and I didn't really feel confident in my ability to do that well. So this will be an area to explore in future research. Overall, this project demonstrates the potential of machine learning and automating stellar classification with room for further improvement using these more advanced techniques. And that's it. So thank you. Hope you enjoyed.